In this video, we're going to be looking at the empirical rule. The empirical rule is one of the most major concepts in statistics. When you look at the empirical rule, it applies to all normal bell-shaped distributions. Another term that you could see is a mound shape. So mound-shaped, bell curve, normal, these are all synonymous descriptions of what they're talking about when they talk about the empirical rule. So the empirical rule, the 60, 95, and 99.7, these are actually percentages. So this is 68% for one standard deviation, then 95% of the data lies within two standard deviations, and then 99.7% of the data lies within three standard deviations. So what this is telling you, it's telling you the area under specific regions of a bell curve, as long as the data is normal. Now I'm going to get into all of this in a minute, but I would say this particular diagram is extremely important. So if you are not printing out note packets, I would pause the video and write down this diagram and make it pretty large. So I'm just going to pause for a second. And now once you have that written down, we're going to talk about all the particulars, but I would like to just talk to you about where and when you would use a normal distribution. So again, if you want to pause the video real quick and write this down, you can. Examples of a normal distribution occur for scores on assessments, heights, weights, speed, body temperature levels, and Minko. When they talk about scores on assessment, they mean general scores in a classroom are often normal. We always look at the average score being in the middle, and then typically more scores above and then below, but particularly on standardized tests such as the SAT. All right, over here is a diagram. So we have our mound-shaped bell curve. Mu is our Greek letter mu, which means, just a refresher, is our population mean. And then this is sigma, the standard deviation. So mu is our mean, and we're going to mark the mean in the middle of the bell curve. And then to the right, you're going to go one standard deviation above, so mu plus the standard deviation, mu plus two standard deviations, mu plus three standard deviations. You're going to go up 1, 2, and 3 standard deviations. And then same thing in the other direction. You're going to go below 1, below 2, below 3. Within one standard deviation of a mean is 68% of the data, which means because this is your halfway point, half of the data is above the mean and half the data is below the mean. So we can take the 68%, the 95%, the 99.7% and divide those by 2, and that would give us the values to the right and then to the left. So if you take 68% divided by 2, you're going to get 34% is within one standard deviation above the mean, from the mean, and from the mean to one standard deviation below is another 34%. So when you put the two 34% together, you're going to get 68%. There's quite a big jump going from 1 to 2 standard deviations. So for just 2 standard deviations, you would have 95% of the data is within that range from the mean. And if you take 95 and divide by 2, you're going to get 47.5%. So if you look here, this is talking about from here to here. And then all that they're doing is they are subtracting the 47.5. So they're going from here to here to get 95%. Okay. And as they're looking there, if you subtract 0.34, you're going to get the 0.135. So this is the extra. All right, and then if you have standard deviations above and below the mean, you will go 99.7% of the data. So that is this amount here divided, this is the 99 7 by 2 as a decimal, not as a percent. And you can kind of see how they're sectioning each area. So if you take the 0.4985 and subtract the 0.475, that extra little bit over here is very small. These two numbers together add up to the point. I think I might have said something wrong there. So if you look at the 0.5, and I'm going to go ahead and do this. So 0.5 minus 0.4985, you get this little tiny remainder out here. As a percent, that would be 0.15% is one tail. So two tails would be the 0.3 or 0.3% or 1 minus 0.997. Oops, 1 minus 0.997. This would be both tails together. So that would be outside of 3 standard deviations. Okay, so hopefully that makes some sense to you. So let's look at this in the context of a few problems. So for the first example, and from this point forward, I would just keep drawing in the bell curve with your markers for the center and then adding 1, 2, 3 standard deviations above, and then 1, 2, 3 standard deviations below. We're also going to shade so we know what we're looking for. So the National Health Survey found that the heights of men have a bell-shaped distribution with a mean of 69 inches. So this is going to go in the middle. So our 69 inches in a standard deviation. So our mu is inches. And our standard deviation of 2.8 inches. It has a standard deviation of 2.8 inches. Draw a bell-shaped distribution with proper labels for this data. So we're looking at the heights of men, and now we're going to take the 2.8, and so all I'm going to do is I'm going to take 69, I'm going to add 2.8, I'm going to add 2.8 again, and I'm going to add 2.8 again. And you're welcome to kind of do that all at once to get your 3 values. So I'm going to say that I am adding 2.8, and then I'm going to write in these values. So this is 71.8, 74.6, and then 77.4. These are inches. Okay, so this is the height of a man. All right, and now we're going to do the same thing to the left. So now we are going to subtract 2.8 inches. So we have 69 minus 2.8 minus 2.8 minus 2.8. Okay, and now I'm going to write in these values. So I'm going to write in the 66.2, the 63.4, and then the 60.6. All right, and now they are asking what percentage of men have heights between 60.6 and 77.4 inches. So you are starting here, and we're going all the way to here. So this is the area that I'm going to just kind of lightly shade in. Okay, and then just a reminder, this part here is the 68%. This part here is the 95%. And then from 3 standard deviations above and below, we're going to be getting our 99.7% to answer this question. So here, 1 standard deviation above and below is 68%, 2 standard deviations above and below is 95%, and then 3 standard deviations above and below are 99.7%. So right now, as we're working through our data, we will be looking at values that kind of fit right on the benchmark. And then we can look at another way when the values don't exactly lie on 1, 2, or 3 standard deviations. So the phrase that says within 1 standard deviation of the mean means that you're talking about the mu plus or minus 1 standard deviation. If you are 2 standard deviations within the mean, you have your mu plus or minus 2 standard deviations. And then within 3 standard deviations, you have the mean. And then you could go up 3 and then below 3. All right, we're going to go on to example 2, which is on page 2, following along in our packet. And so for this one here, the next 3 examples are going to be looking at different parts of our mound of our normal distribution, and I would like to kind of guide you so you know what to look for when. All right, so in this example, just a reminder, we're doing 60%, 95%, and then 99.7%. This is called the empirical rule. This is 1 standard deviation above and below the mean, 2 standard deviations above and below the mean, and then finally 3 standard deviations above and below the mean. All right, for example 2, the lifespans of seals in a particular zoo are normally distributed. The average seal lives 15.5 years. The standard deviation is 2.2. Use the empirical rule to estimate the probability of a seal living between 19.9 and 22.1 years. So if you feel comfortable labeling your mound, by all means, go right ahead and do that. Your mean is going to be 15.5. And now we're going to be adding 2.2 to the right, and we're going to subtract 2.2 to the left. And we're going to do the same thing we just did a minute ago. So I have 15.5 plus 2.2 plus 2.2 plus 2.2. I would recommend that you do it in stages, one at a time. Otherwise, it's just going to take a little bit longer to do your calculations. Okay, so now I'm going to write those in, and I'm going to kind of write them in on an angle. So 17.7, 19.9, and then 22.1. And then you would do the same thing to the left. So 15.5 minus 2.2, minus 2.2, minus 2.2. Oops, 15.1 minus 2.2, minus 2.2, minus 2.2. Right away, I did something wrong there. All right, so you get 13.3, 11.1, and then 8.9. Okay, and now once you have all those labels down, I'm going to darken this just a little bit. They are asking you to estimate the probability of a seal living between 19.9 and 22.1 years. So I am looking at this part here of my distribution. All right, and just a reminder, I'm going to pull this up and put it right next to this. And so if you want to keep referencing this, by all means you can. So this is looking at, I think I highlighted this one. Let's see, one pink, one was yellow. I did pink to the right. So this one's pink, and this one is yellow. And we are looking at the difference between those two. So you can look at half of the 99.7% and half of the 95% and do the difference. This chart actually tells you. So you look at 0.4985 and 0.475. The difference here is going to be that 0.0235. So this part here is 0.34%. No, this part here is 34%. So 34 goes from here to here. Try to clean that up. So this is 0.34 from here to here. This part here is the 0.475, and then from here to here is the 0.4985. So you're just going to take the 0.4985 and you're going to subtract the 0.475, and then that will give you this. So if you want to multiply by 100, it would be 2.35%. And that's how you would do that particular example. Okay. Another way you can think of it, there's lots of ways you can kind of work that out. Another way you could do it is saying that the whole upper half is 50%, and you could subtract out the 0.475 and then subtract out that little tiny bit of the tail here, and you should get the same number doing that as well. So let me just show you that. So if I did 0.5 minus 0.475 minus 0.15, oh, I'm not in the right unit, sorry. All right, so this is doing 50, so this is 50%, and then, so this was as a percentage. Or I could have done this as 0.0015. So 50 minus 47.5 minus 0.15. So that's as a percentage I can do it. Or I could have done 0.5 minus 0.475 minus 0.0015, and I can show you that too. So 0.5 minus 0.475 minus 0.0015, and I get the same thing. So this one's as a decimal, the 0.0235, and then this one's as a percentage. Okay, so you can get it either way. All right, we're going to do 2 more quick examples, hopefully. All right, for number 3, the lifespans of lions in a particular zoo are normally distributed. The average lion lives 13.4 years and has a standard deviation of 1.6. Use the empirical rule to estimate the probability of a lion living longer than 16.6 years. So we're going to go ahead and put our mean here, the 13.4. Now we want to keep adding the 1.6 and then keep subtracting the 1.6. I'm going to try not to mess up on my calculator. I'm not doing too well today. All right, so I have the 13.4, and I'm going to subtract. Oops, let's start with that. I'm going to add 1.6. See, I'm not doing too well. 13.4 plus 1.6 plus 1.6 plus 13.4 plus 1.6 plus 1.6 plus 1.6. All right, so I have 15, 16.6, and then 18.2, and I'm going to repeat the other way. So I have 13.4 minus 1.6 minus 1.6 minus 1.6. So this is 11. So I have 11.8, and you could have, of course, paused the video and tried to find these yourself if you had wanted. Okay, so I have 11.8, 10.2, and 8.6, and now you are asked to estimate the probability of a lion living longer than 16.6 years. So this is 2 standard deviations above the mean, and we are looking at this general area. Okay, so remember, the whole upper half is 50%. Okay, and if you remember, 60%, 95%, and 99.7%, you're going to take half of 90, and you're going to get 47.5%. And if you can recall doing some area problems for or kind of like donut problems, anytime you maybe had something where you had a larger area and you subtracted a smaller area, you're really doing the same thing. So I know in geometry, a lot of us had done this, where you would take the total area, say it was 10 centimeters squared, and let's say this is 8 centimeters squared, you would just do the 10 minus the 8 to get 2 centimeters squared for the donut area. It's really the same thing here. So you have half of the distribution, we're taking out half that's not included, and you subtract to get the remaining. So this time I did it as a percent, and you're going to get 2.5%. Okay, and let's look finally at example 4. And this is a very small percent for both 2 and 3, so you're looking at just this tiny little bit way above. So the next one's actually going to be kind of the reverse. So for example 4, the quiz scores for a science class are normally distributed. The average quiz score is 78 with a standard deviation of 5. So since we don't have decimals, that's going to make it a little bit easier. And we want to figure out the probability that you estimate the probability of a student earning a quiz grade higher than 68%. So we're going to look at that. All right, so for here, let's go ahead and put our labels on. All right, so I have 78, and I'm going to add 5. I'm going to add 5. I'm going to add 5. So we're going to get 83, 88, and 93 for 3 standard deviations above. And then I'm going to subtract 5, I'm going to subtract 5, I'm going to subtract 5. So I get 73, 60, and 63. All right, now this is saying higher than 68%. Now don't be confused because they're not talking about the 68 here. They're talking about a score of 68. So we want to figure out what's the probability that the student is getting a grade higher than 68%. So this is 2 standard deviations below the mean. So we had just done that calculation a minute ago. You would remember take 95 and divide by 2, and you're going to get 47.5% is the amount between the mean and 2 standard deviations below. Above the mean is 50%. And so you could just add those two numbers together. So since 68% isn't a very good score, especially since 70 is your mean, most of the students would be getting a score higher than 68. Another way you could think of it is looking just at this tail here. So you could also have done, you could have used your little chart that I kind of showed you at the beginning. And if I come over here, we are looking at this part here, but I think that I had added the 0.0015. You would have to add, because this is also 0.0015, you would have to add these two numbers together to get the amount not included, and then you could have done 1 minus 0.0235, because now I'm in decimals, and then minus 0.0015. So 1 minus 0.0235 minus 0.0015, and that would give you the 0.975. So that's the same thing as a decimal, and then you can multiply by 100 to get the percent. There is more than one way to answer these questions. So you can calculate your percentages a variety of different ways. You just want to use the chart as your guide. And I hope this helps you understand the empirical rule. It is a major concept for statistics. Remember, 1 standard deviation is 68% above and below the mean. 95% is 2 standard deviations above and below the mean. And then 99.7% is 3 standard deviations above and below the mean. Thanks for watching.